BigSoftEd presents Russian Peasant Multiplication. In the BigSoftEd video on long multiplication, one of the four methods shown barely gets a mention. That's because it's somewhat different to the other three.
One of these things is not like the other. One of these things just doesn't belong. Can you tell which thing is not like the other before
Well, yeah, it's this one. These days it's more a curiosity than a serious method for multiplying large numbers. But if you're already confident with the lattice or long multiplication methods, you might find this one interesting to compare. It's unusual because it lets you multiply large numbers without needing to know your times tables. But you do need to be very good at halving, doubling, and adding up. It's known as Russian multiplication, or peasant multiplication, or even Russian peasant multiplication. But in this video I'd like to propose an alternative name: Matryoshka Multiplication. Here's what you do. Start with the numbers you're multiplying at the top of the page. As multiplication is commutative, you can swap the numbers around if you want. You probably want the smaller number after the time sign. Now halve this second number, writing the answer beneath it. Keep halving, writing the number underneath each time. Half of 11 is 5.5. However, you don't bother with any halves in this method, so here we just write down 5 and forget the half. Half of 5 is 2.5, so again we drop the half and just write 2. Eventually you'll always get down to 1, which means you've finished with the halving step. It might seem odd that we're just throwing away halves like that. How can a method give a correct answer if it has such disregard for accuracy? And yet it does, which might make this method sound like magic. It isn't magic. If you're interested in why the halves don't matter, the second part of this video looks at why the method works. Meanwhile, we turn our attention to the first number in the calculation. This one we have to double, and we have to do this as many times as we halve the other one. So double the number and write the answer beneath, but keep it in line with the numbers in the other column. This way you'll know you've finished when you write an answer in line with the 1 at the bottom. Neatness, as ever in mathematics, is more than just for show. Doubling can get tricky as the numbers get large very quickly. Look for shortcuts and tricks. For example, doubling 212, you can double the 12 to get 24, then double the 2 to give you 424. Once you're done with the doubling, look at the two columns of numbers. For every even number in the column on the right, where you halve numbers, you can cross out the number in the column on the left, where you doubled the numbers. And this counts for the very first line where you wrote out the question. Finally, you add up the remaining numbers in the column you doubled, those that haven't been crossed out. It's usually a good idea to copy them to a new part of the page. The final sum is the answer to the original multiplication. You can check it using your favourite pen and paper method or a handy silicon brain. Or try swapping the numbers over and see how the working is different, but the answer is the same, as long as you haven't made a mistake. And that's Matryoshka multiplication. But why does it work? Why does it work? If you want to know, keep watching. The first thing to understand is what happens when you double a number. Doubling is the same as multiplying by 2, and if you double a number twice, you've multiplied the original number by 4. Double it again and you've multiplied by 8, then by 16, 32, and so on. Similarly, the number being halved is being divided by 2, then by 4, by 8, 16, and so on. Now you might recognise these numbers as powers of 2. It doesn't matter if you don't, but that's what they're called. And for completeness we should put in the ones at the top. The curious thing is that in the rows where the halving gives us an odd number, those powers of 2 add up to the original multiplier, 44 in this example. 4 plus 8 plus 32 is 44. And the Matryoshka method says to add up the numbers in the doubling column that match these powers of 2. So that means we're adding up 53 times 4, 53 times 8 and 53 times 32. Which is the same as adding 4, 8 and 32, then multiplying by 53. So you see, Matryoshka multiplication still uses the distributive rule just as the box, lattice and long multiplication methods do, but it's harder to spot. The distributive rule is discussed a bit more in the BigSoftEd video on long multiplication. By the way, if you know about binary numbers, you might also like to know that writing ones and zeros next to the odd and even numbers you get when halving the multiplier gives you its binary equivalent. But why exactly does halving the number you're multiplying by and only using the odd rows give us the powers of 2 that add up to the number?
But why?
Let's dig a little deeper. Remember when we divide one number by another, such as 44 divided by 2, we're asking how many 2's are there in 44? Or how many 2's can we split 44 up into? Well, let's start at the beginning, with 44 divided by 1, which means how many 1's in 44? Well, unsurprisingly, the answer is 44 1's. For 44 divided by 2, we can pair those 44 1's into 22 2's. For 44 divided by 4, pair the 22 2's into 11 4's. Now we have an odd number of 4's, which means when we come to pair up for 44 divided by 8, we can pair 10 of them to get 5 8ths, but 1 4 is left over. Which makes sense. 44 divided by 8 is 5 remainder 4. And there's another odd number, 5 8ths in 44. So when we divide 44 by 16, only 4 of those 8ths can be paired up to make 2 16s, with an 8 and a 4 left over. Again, that's what we expect, as 44 divided by 16 is 2 remainder 12, 12 being 8 plus 4. Finally, for 44 divided by 32, those 2 16s are paired to make 1 32. That's why halving, continually dividing by the next power of 2 and only keeping the rows with an odd number for an answer, gives us the correct powers of 2 that add up to the multiplier. And that's how Matryoshka multiplication works. Look at those dolls. They're so full of themselves.